Right. So now we are discussing groups of permutations. This is what we went over last time. We actually calculated all elements in D3, the dihedral group of order 6. Right? So it's the group of symmetries of an equilateral triangle. We'll briefly go over this one, then we'll calculate each and every element in D4 as well. That would be the group of symmetries of the square. Right. So D3, in here we take rho I to be rotation. So these rotations are taken clockwise about the origin. And then we take mu I to denote reflections in bisectors of angles. So these bisectors will be lines of symmetry, right? So one we have through the vertex 1 and the origin, the other one through the vertex 2, the origin. Then we have the other line through the vertex 3 and the origin. Then we calculated rho 1, which is the first rotation that you see by an angle of 2 pi over 3 about the origin. In that case, we will be sending 1 to 2. When we do that, 2 goes to 3 and 3 will be going to 1. So this will denote that permutation, right? Then the second one, a rotation by an angle of 4 pi over 3. 2 times this angle. So we are, once you start rotating, 1 will not stop at 2, it will simply go to 3. In that case, 2 will be going to 1, 3 will be going to 2. So this is the other rotation. Then you see row 3, you take the rotation by an angle of 3 times 2 pi over 3, which is an angle of radian 2 pi. So you're taking this 2 pi rotation about the origin. 1 will go all the way and come back to itself. So 2, 3, they will come back to their original spots. What you have as row 3 would be the identity permutation, right? The identity. Okay, so from these are the 3 distinct rotations we have for this group. Then starting off with mu1, taking this to be the reflection about the line of symmetry through 1 and the origin. We have 1 to be fixed. Then we are sort of like taking the reflection about this line. In that case, 2 and 3 will be swapped. So 2 will go to 3, 3 will go to 2, and 1 will be fixed. Then mu2, we have taken this to be reflection about the symmetry that we get when we consider the reflection of this triangle about the line through the origin and the vertex 2. Then we have mu3. So we have these distinct elements, right? And these are the only 3 lines of symmetry for the triangle. So the equilateral triangle, we have these distinct elements in D3 where one resembles the identity. Right. Now observe, we already know that the order of row is 3. Why is that? If we look at this one, right? And if you compare row 1 and row 2, how do we get to row 2 from row 1? Now, row 2 is the rotation that you get or the symmetry that you get if you rotate it by an angle of 4 pi, which would be 2 times 2 pi over 3 about the origin. That means first we perform this rotation. Bring 1 and about the origin, we perform a rotation by an angle of 2 pi over 3. Then the same rotation, now in this case, 1 will be at this spot. So you are performing the same rotation over here. That means you are taking 2 of these row 1s. So 2 of these row 1s will equal row 2. You can actually see this by simply calculating row 1 square. Now in this case, what is our binary operation? That would be function composition, right? because these permutations are functions, right? So first, what we are going to do is we will calculate rho 1 squared. That means we have to take the composition of these two functions of the same function, right? Rho 1 by itself. What do we get? We start with this one. So we want to see where 1, 2, 3 will be sent to in this composition. So 1 goes to 2 over here. We always start with this, the function that's on the permutation that's on the right in the composition, right? 1 will be sent to 2, 2 will be sent to 3. So in the composition, 1 will eventually go to 3. Now go back to 2 here. 2 will be sent to 3, 3 will be sent to 1. So 2 will be sent to 1. 3 will be sent to 1 and 3 and 1 will be sent to 2. So 3 will be sent to 2. If you go back, you see row 2 is exactly that, right? So this is equal to row 2. Now we calculate row 1 cube. That means we are going to take rho 1 squared times rho 1. This times, what do we mean by this product? It's actually the function composition of rho 1 squared and rho 1. So rho 1 squared we know to be rho 2. So I will write this. And then rho 1. Okay, now when we take the composition, see, 1 will be, we want to see where 1, 2, 3 will be in this composition. 1 sent to 2 and 2 sent to 1. So 1 will be going to 1. 2 sent to 3 and 3 sent to 2. 2 will be going to 2. 3 sent to 1 over here. 1 is sent to 3. What we get over here is the identity. And this is the smallest possible power of the smallest positive power of rho 1 such that rho 1 raised to this number gives you the identity. By definition, 3 is its order. So we see that order of rho 1 in this group is 3. Order of rho 1 in this group is 3. Not only that, it's easy for us to see that from this itself, right? From this itself, we have rho 1 cube to equal 1, right? So I can write this as rho 1 squared times rho 1, which equals 1. This tells you, by definition, the inverse of rho 1 must be this function that you see over here, this permutation. So inverse of rho 1 is what? Rho 1 squared. In other words, this rho 2 that you see over here. Inverse of rho 1 is this. Now, from these rotations, we see 3 distinct elements in D3, all of which are given in terms of rho 1. 1 is the identity that is given as rho 1 cube. And then we have rho 1, which simply is rho 1. Then we have rho 2, which is given by rho 1 squared. So all these, the first 3 elements that you see in this group, we actually haven't shown that it is a group yet, but we will show all the definitions are satisfied. All the axioms are satisfied, sorry. So these 3 distinct elements are simply given in terms of rho 1. Right, now let's go to mu 1. Mu 1 is simply the reflection about the line of symmetry which goes through 1 and the origin. If I write it over here, mu 1. Now let's calculate mu 1 squared, right? Let's see whether we can derive the rest of the elements by simply looking at mu 1. Now we know by simply considering any power of rho 1, we cannot get any other element in this group. Why? Once you have rho 1 cubed to be the identity, if you calculate the power of rho 1 to the, if you calculate rho 1 to the power of 4, you can write it as a remark, I'll put it over here. Rho 1, 4, you can write as rho 1 cube times rho 1. Rho 1 cube is the identity times rho 1. Because this is the identity permutation, identity function. So when you take the composition with that, you get this function itself, right? This is why we call this the identity of this given group. Okay. Therefore, for any other element that to any other power of rho 1 will end up being either the identity rho 1 or rho 1 squared. So these three are the only distinct elements that you can take in terms of rho 1. Now let's consider mu1 squared. This is mu1 times mu1. When I say times mu1, when I say times, I mean function composition. Mu1 is given by, sorry, it's over here. 1 fixed, 2 and 3 interchanged. So we have now let's see, 1 goes to 1 over here, 1 goes to 1, 1 will go to 1. 2 goes to 3 and 3 goes to 2. So 2 will go to 2. 3 goes to 2, 2 goes to 3, 3 will go to 3. What you have is the identity. What you have is the identity, right? So we see that the order of mu1 is 2. Not only that, since mu1 squared is equal to the identity, we can write mu1 times mu1 equals the identity. This tells you the inverse of mu1 is itself by definition of an inverse, right? Inverse of mu1 is itself. Now, if you take mu1 cube, right? As a remark, I'll put it over here. If you take mu1 cube, you can write this as mu1 squared times mu1. Mu1 squared is simply the identity times mu1 ends up being mu1. So the only distinct element that you can take out of mu1 is simply mu1. If you, by considering powers of mu1, I mean to say, would be mu1, because as soon as you square it, you take its second power of mu1 raised to 2, you get the identity, right? And for cube, for its fourth power, you will alternate between mu1 and the identity. So the mu1 does not generate any other distinct element in the group. Now, what I'm going to do is, we know that rho 1 is an element, mu1 is an element. I'm going to take the product of the two. We will simply take the product of the two. Keep it over here. Let's take mu1, rho 1, right? Rho 1 is given by sending this to 2, 3, and 1. Now let's calculate, let's find this composition. 1 goes to 2 over here, 2 goes to 3. So 1 will go to 3. Then we have 2 goes to 3 and 3 goes to 2. 2 will go to 2. That means 2 is fixed. Now we are looking at the reflection over the line of symmetry, that goes through the vertex 2 and the origin. 3 goes to 1, 1 goes to 1, so 3 will go to 1, right? 2 is fixed. So the line of symmetry for this particular reflection, this particular symmetry is through 2 and the origin. This is equal to what? If we go back to all our elements, mu2. So now observe, we have taken another distinct element in this group by mu1 and rho 1. By mu1 and rho 1. Now let's calculate mu1 and rho 1 square, the other possibility for us. This would be 1, 2, 3, 1, 3, 2. One goes to 3 and 3 goes to 2. So 1 will go to 2. 2 goes to 1, 1 goes to 1. This will go to 1. 3 goes to 2, 2 goes to 3. 3 fixed. Now this is mu 3. This is the symmetry that we get when we reflect the equilateral triangle about the line that goes through the vertex 3 and the origin, in which case 3 will be fixed, right? Now observe once again the last element in our group, right? If I write out these elements, we have D3 to contain the identity, row 1, row 2, mu1, mu2, mu3, right? Now what I'm going to do is replace all these elements. 1, I will leave it as 1, but we understand this is simply, just to denote that it's the identity. This is row 1 cubed. So from the rotation, you get this one. Row 1 square. Then you have mu1. Mu2 is mu1 row 1 and mu1 row 1 squared. Right? Right. We have gotten all the elements in this group simply in terms of row 1 and mu1. Simply in terms of row 1 and mu1. So we can see that every element in this group is generated by row 1 and mu1. Every element in this group is generated by row 1 and mu1. Okay? So in other words, we can say that row 1 and mu1 are generators of D3, right? Those are the generators of D3. So every element in D3 takes the form, so we can write in D3 is of the form mu1k row 1I, where k is either 0 or 1, and I can take the values 0, 1, and 2. So, all right, I is between 0 and 2, including the 2. Right? If you look at the identity is given by mu1 power of 0, row 1 power of 0. Row 1 is given by mu1 power of 0, row 1 power of 1. Row 1 squared is given by mu1 raised to the power of 0, row 1 squared. Mu1 is given by mu1 raised to the power of 1, row 1 raised to the power of 0, likewise. Right? Okay. Right. Now, like I said, the order of row 1 is 3, order of mu1 is 2. And inverse of row 1 is row 1 square. Inverse of mu1 is mu1. Identity of this group is 1, which is this identity function, identity permutation, right? We have seen that if you remember S3, right? In there we saw the identity permutation or the identity function being the identity for the group. Says it's very similar over here because all these elements are permutations of these vertices which are labeled 1, 2, 3. So you think of it as a function from 1, 2, 3 to 1, 2, 3. It's a permutation, right? And the binary operation over this group is function composition. This is the identity, and because each element is written in terms of rho 1 and mu 1, we only need to find inverses for rho 1 and mu 1. Inverse of rho 1 is given by this, inverse of mu 1 is given by this, both of which are elements in the group, right? And if you want to find the inverse of each and every element in the group, there is a relation, a specific relation that these elements satisfy. I will simply list them. We can use it. We have RS2 equal SR inverse, right? And using mathematical induction and extending this, we see that for any I, we have RIS to equal SR negative I, right? And then now say you want to find the inverse of mu1 rho 1, and observe that inverse of rho 1 is rho 1 squared. Then what is the inverse of this element? Rho 1. Inverse of mu1 is itself. Inverse of the identity is also itself. If we go to mu1 rho 1, let's find the inverse of mu1 rho 1. Let's find mu1 rho 1 inverse. We know this is equal to rho 1 inverse composite mu1 inverse, right? We have seen these properties when we were discussing properties of the identity inverse and all that at the very beginning of this course. Now, rho 1 inverse is simply rho 1 square. Mu 1 inverse is simply mu 1. Now, go to this relation. This says if we have a power of, here R resembles rho 1, S resembles mu 1. So, what I'm going to do is I will write it as rho 1 mu 1 is equal to mu 1 rho 1 inverse. Rho 1 I mu 1 is equal to mu 1 rho 1 raised to the power of negative I. Right, so we are going to use this. Now, if you compare it with this term that you have, I is 2. So, consider using this relation, I will write rho 1 squared mu 1 as mu 1 rho 1 negative 2, right? This is what? Mu 1 rho 1 squared inverse of rho 1 squared. We know the inverse of rho 1 now. Over here itself, from here we can deduce the inverse of this is what? Rho 1. So this will simply be replaced by rho 1. We have mu 1 rho 1. So the inverse of mu 1 rho 1 ends up being the element itself, right? You can similarly find the inverse of mu 1 rho 1 squared. We can simply find mu 1 rho 1 squared inverse. This is what? Rho 1 squared inverse mu 1 inverse. The inverse of rho 1 squared is rho 1. This is mu 1. This is equal to, once again going to this relation, I will replace rho 1 mu 1 by mu 1 rho 1 inverse, right? Because we have no such element in the group. We are trying to see whether it ends up being one of these elements, right? It will be this one. And rho 1 inverse is simply what? Rho 1 squared. So the inverse of this element ends up being this one. Now you see in this group, even though I called it a group, we never proved all these axioms. The identity permutation over here is the identity of the group, right? It's closed under the binary operation no matter which element you take, and you take the composition of those two, it will end up being an element in the set, right? It will end up being an element in the set. And then For each element, we found the inverse, which is also an element in the set itself. The associativity holds because it holds for function composition. This is a group under function composition. So this is all about D3. Right. Now let's quickly go over D4. So now we are trying to find the group of symmetries of the square. Let me start by taking the square. Suppose this is the origin. Let's name this vertex, label it 1, 2, 3, 4, right? And we have 4 lines of symmetry. This line that goes over the main diagonal, then this off diagonal, then the midpoint of the two opposite sides. This is one line and this line. So these are the lines of symmetry, right? And we can get symmetries by rotating it as well. Now, we have an angle of pi over 2 radian between these two lines of symmetry, right? So when you rotate it by an angle of pi over 2, you can move 1 to 2, 2 to 3, 3 to 4, and 4 back to 1, right? So in here, in this group, see what I'm going to do. We will take row 1 to be the rotation clockwise about the origin by pi over 2 radian, I'll put. Then let's take mu1. This will be the reflection about the line of symmetry through vertex 1 and the origin. Origin is over here. Now see, we will write all elements in D4 simply using row 1 and mu1. Right? And you will see for any n, Dn has two generators, row 1 and mu1, where row 1 would simply resemble a rotation clockwise about the origin by 2 pi over n radian, and mu1 will be the reflection about the line of symmetry through vertex 1 and the origin. Okay? Right. Now, first one we find row 1. We have 4 vertices now, right? One, if you rotate this by an angle of 2 pi, 1 will come to 2 and the rest will follow. 2 will go to 3, 3 to 4, 4 to 1. So we have 2, 3, 4 and 1. This is the permutation. This is row 1. Now see, when I calculate row 1 squared, that means row 1 composite row 1. What does this actually mean? This means you start with this original, the square where vertex 1 is over here, rotate it by an angle of pi over 2, then again rotate it by an angle of pi over 2. So all in all, we are actually rotating this by an angle of 2 times pi over 2. In other words, by an angle of pi radian. So 1 will go all the way to 3, 2 will go all the way to 4, 3 will go all the way to 1, and 4 will go to 2, right? If you don't really write it as two functions, by simply looking at the picture, you can get this permutation. 1 will go to 3, 2 to 4. 4 will go to, sorry, 3 will go to 1 and this to 2, right? Even if you write row 1, composite row 1, this function itself, you find the composition, you will end up with this one. Now let's find row 1 cube. This is row 1 composite, row 1 composite, row 1. What does it mean? This means we start with this, right? 1, 2, 3, 4, they are at their respective original places, they are their original spots. First, we take this row 1. This means we are rotating this by an angle of pi over 2. Now 1 is here. Now go to this next permutation. We rotate this by an angle of pi over 2. 1 comes here. Now, corresponding to this last row 1 that you see in the composition, rotated by an angle of pi over 2. 1 will go to 4. So 1 will go all the way to 4, 2 will go all the way to 1, 3 to 2, and 4 to 3. We have our permutation written down as 4, 1, 2, and 3. Now let's find row 1 raised to the power of 4. Once again, go to this. Now we have to rotate this by an angle of pi over 2 4 times, right? 4 times. So all in all, what is the angle that we are taking? Is the angle of rotation about the origin? 4 times pi over 2. That is 2 pi. So we are taking the rotation by an angle of 2 pi, right? Start at 1, rotate all the way back by an angle of 2 pi. We are back at 1, right? So we understand what I get over here is the identity, which I will simply denote by 1. So from here itself, we see that order of row 1 is 4, right? And these are 4 distinct elements in the group. Row 1, its square, its cube, and then we have the identity, which is equal to row 1 raised to the power of 4, which is also the same as taking row 1 raised to the power of 0, right? Um, and then row 1 inverse is simply row 1 cube. Row 1 inverse is simply row 1 cube. Why is that? Because of this equation, we have row 1 squared is equal to row 1 cube times row 1, which is equal to the identity. So the definition tells you then the inverse of row 1 must be row 1 cubed, and inverse of row 1 cubed must be row 1, right? And then what is the inverse of row 1 squared? It must be itself. Why is that? Once again, we are going to this equation, and inverse of 1 is 1, which I will not write. We all know the inverse of the identity is the identity. We can write as row 1 squared times row 1 squared, which is equal to 1. This tells you inverse of row 1 squared, which we will simply write as row 1 raised to the power of negative 2, is row 1 squared, is itself, right? So from this equation itself, we have gotten all the inverses. Now let's go to mu1. Mu1 will be the reflection about the line of symmetry through vertex 1 and the origin. So let's go with mu1. We have 1, 2, 3, 4. We want to see where it goes. If you go back and look at the reflection, the line of symmetry we are talking about, it's the line through 1 and the origin. Or in other words, the line that goes, it's the off diagonal, the line that goes through 1 and 3. So you hold this square by this line and reflect it. So you flip it. Once you flip it, 2 will take the place of 4, the vertex 4. 4 will be in place of 2. 1 and 3 will be fixed. They will not change their position, right? So 1, 3 will be fixed, 2 will go to 4 and 4 will go to 2. This is our mu1. Now let's calculate mu1 squared. This will be mu1 composite mu1. What does it mean? We have to apply mu1, the operation or the reflection about this line through the vertex, through this line of symmetry twice. That means first we are with this original picture where these labels, where these vertices are at their respective places. 1 here, 2 here, 3 here, 4 here. This is the line of symmetry. First, I will take the reflection about this line once. So when you reflect it, 2 will go over here, 4 will be here. So at this one reflection, when you take mu1, instead of 2, you have 4 here. Instead of 4, you have 2 here. Now what do we do? In the composition, we have to do the same reflection once again. Mu1 composite mu1. So now we reflect it again about the same line. What does it mean? You are swapping these two vertices again. So the second time around, 4 that was here due to the first reflection will go back to its original position. 2 that was here due to that first reflection will come back to its original position. So we are back at the original position, right? So this will give you, and 1, 3 will never change. We have 1, 2, 3, 4. It's easy to see this is the identity. So we understand order of mu1 is equal to 2, and the inverse of mu1 is itself, right? Now we are going to calculate mu1 rho 1. Now we are going to calculate mu1, mu1 rho 1. Mu1 is given by so what happens over here, if we think about it, if we don't really write these elements, I will just, because I started off writing it, I will put it over here. Now, if you look at mu1 rho 1, this means first we take the rotation rho 1, then reflection mu1. So if you go back to this, first we rotate this by an angle of pi over 2. 1 will be here, 2 will be here, 3 will be here, 4 will be here. Then we take this line of symmetry, right? The line of symmetry is this now, right? Even though we have shifted the labels, this is our line of symmetry. Now what do? We reflect it over this line. In this case, we have elements 4 and 2 to be fixed. 1 and 3 will be swapped, right? You can see this by actually computing this. We have 1 goes to 2 and 2 goes to 4. One goes to 2 and 2 goes to 4. Did I write it? 2 goes to 3 and 3 goes to 3. 3 goes to 4 and 4 goes to 2. 4 goes to 1 and 1 goes to 1. Right. Okay. And then we will calculate mu1 rho 1 square. Now what happens over here? Now, if you go back to this one once again, what I said earlier, because when I said these elements will be fixed, they are fixed in their places after that rotation. So we have to keep that in mind. When you rotate it by an angle of pi over 2, 1 will be here, 3 will be here. When you do the reflection, 1 will come here and 3 will be here, right? 4 will be in this place, 2 will be in this place. So when you take the permutation, when you look at these labels, you will see 4, 3, 2, 1. right? That is why we have this permutation. Okay, now this other one, mu1 rho 1 squared. In this case, we have mu1, 1, 2, 3, 4. Then rho 1 squared is 3, 4, 1, 2. Right. When you take the composition once again, you see 1 goes to 3, 3 goes to 1 goes to 3 and 3 goes to 3. 2 goes to 4 and 4 goes to 2. 3 goes to 1 and 1 goes to 1. 4 goes to 2, 2 goes to 4. These two fixed, the other two swapped, right? Then finally we calculate mu1 rho 1 cube. That's the other distinct rotation we have. Okay. Um, if we calculate this, we will get 1 goes to 4 and 4 goes to 2. 2 to 1 and 1 to 2. Then we have 3 to 2, 2 to 4. 4 goes to 3, 3 goes to 3. Now you see, we have we have 4 lines of reflection, right? 4 lines of symmetry over here. This first one resembles to mu1. Then, if you go look at mu1 rho 1 square, even though we understand what's happening over here, is we are rotating it twice by the angle pi over 2, then taking a reflection about this line, this fixed line. But what does it mean with respect to the other 4 lines? See over here, 1 is being replaced by 4, 4 is being replaced by 1, 2, 3 once again swapped. That means, I'm referring to this one, we have taken the reflection about this line, which goes over the midpoints of these two opposite sides. When you reflect it, 1 will replace 4, 4 will replace 1, 2 and 3 will be swapped. That is what you see over here. If you come to this one, 2 is fixed, 4 is fixed. So obviously we are talking about this line, reflection over this line, where 2, 4 will be fixed, the other 2 will be swapped. Now, when you come to this last one, 1 and 2 have swapped, 3 and 4 have swapped. That means we are taking the reflection about this line. So those are all the elements. We have 8 elements altogether. If you put them in the set, we have D4 to contain the identity rho 1 squared, rho 1 cube, mu1 rho 1, mu1 rho 1 squared, and finally mu1 rho 1 cube. And the relations apply to this group in general, right? If you write dn, if I take rho 1 to be the rotation clockwise. Now, this is for the general case I'm writing because these relations are generally true for any n. Clockwise, it holds for any n, right? Clockwise about the origin by 2 pi over n radian. Then we take mu1 to be the reflection about the line of symmetry through 1 and the origin. Right? Then we have the order of rho 1 to be n, order of rho 1 to be n, order of mu1 to be 2, right? Order of mu1 to be 2. And then the relations. Rho 1, mu1 is equal to mu1, rho 1 inverse. And extending this, we have rho 1I mu1 is equal to mu1 rho 1 raised to the power of negative I. Okay. Okay, now what we are going to do is we are going to compare the groups D3 and S3. We will show that these two groups are isomorphic, right? Comparing D3 and S3. Right, so D3, right, is of order 6. Then we have S3, once again, is of order 6, right? The identity is this identity permutation, same for S3, right? We have this identity permutation, which we denote by this. Then we have row 1, okay, which sends 1 to 2, 3, and 1. Then corresponding to row 1 in S3, we have a permutation where we send the element 1 to 2, 2 to 3, and 3 to 1, which is what? 1, 2, 3. In this cycle, we see that 1 goes to 2, 2 goes to 3, and 3 goes to 1. So these two correspond, right? Not only that, these two correspond. Not only that, row 1. The order of row 1 is 3. Order of this cycle is also 3, which you can verify. Okay. Then let's go to row 1 squared. Row 1 squared, you have 1, 2, 3. This one. This is the permutation where 1 is sent to 3, 3 is sent to 2, and 2 sent to 1. So we have the corresponding cycle. 1, 3, 2. Right? So row 1 squared corresponds to this one. Then we have, these are all the rotations. Then we have mu1. Right? Mu1 is 1 fixed, 2, 3 will be swapped. Right? 1 fixed, 2 will go to 3 and 3 will go to 2, which corresponds to this cycle, where 1 is sent to 1, 2 is sent to 3, and 3 is sent back to 2. Then we have mu1 row 1 to be 3, 2, 1, where 2 is fixed. So this corresponds to the element in S3, 1, 3. Then you go find mu1 row 1 squared. In this case, 3 will be fixed. These will be swapped. So we have 1, 2, right? Now, if you look at mu, right? Order of mu1 is 2. Order of this element is also 2. Right? Order of this element is also 2. Not only that, observe that D3 is generated entirely by row 1 and mu1. Now, if you look at these elements, we understand row 1 has a correspondence to this cycle, mu1 to this one. Now observe, I can write 1, 3, 2 as 1, 2, 3, squared. Squaring means we are taking the composition of this cycle by itself, right? 1 is sent to 2, 2 is sent to 3. So 1 is sent to 3. Then 3 is sent to 1, 1 is sent to 2. So 3 is sent to 2, this same element. So now you see 1, 3, 2. This cycle is generated by this element, which corresponds to row 1, right? And this has a correspondence. Now, I can write it as over here itself, I'll put it. Over here itself, we can put it 1, 2, 3 square. Yeah. This is row 1 square. What you see over here is this cycle square. Now we have mu1 to be this one. Now observe the other one. We can write 1, 3 as the composition of 2, 3 and 1, 2, 3. 1 is sent to 2, 2 is sent to 3. So 1 is sent to 3. 2 is sent to 3 and 3 is sent to 1. Sorry, 2 is sent to 3 and 3 is sent to 2. 2 will be fixed. 2 will be sent to itself. 3 is sent to 1, 1 sent to 1. So 3 is sent to 1. Right? So this element is the same as this, this element is the same as 2, 3, 1, 2, 3. If you compare the two, over here you have mu1 row 1. Over here you have the cycle 2, 3 and the cycle 1, 2, 3, which equals 1, 3. And this ends up being, you can do the calculation and verify this yourself. This will be 2, 3, 1, 2, 3 square. Right? 1, 2, 3 square. Right. Now, if you look at this side, we understand S3, even though it's not a cyclic group, it has two generators now. This can be generated by simply two elements because every element in the group can be written in terms of the cycle 1, 2, 3 and 2, 3. So we understand D3 is generated by row 1 mu1 and the cycle 1, 2, 3 and 2, 3 corresponds to these two elements. S3 is also generated by those two elements. As you can see, all these elements can be written as a product of the two, right? So we see that we know that D3 is generated by row 1 and mu1. S3 is generated by 2, 3 and 1, 2, 3. These two elements. So S3 has two generators, this one and this. Okay, now to see that these two are isomorphic, we need to understand what an isomorphism means between the two groups, right? In order to do that, we will learn homomorphisms. So our next topic would be homomorphisms. Homomorphisms. Okay. Definition. A map P of a group G into a group H is a homomorphism if phi of AB is equal to phi of A, phi of B for all AB in G. Right, so what does it mean? You see over here, phi of AB, a product. What does it mean? If I explicitly denote the binary operations on G and H, if I take G to be the group under the binary operation star, H to be the group under the binary operation, let's take the little circle, then phi from G to H is a homomorphism. This function is a homomorphism. If phi of A star B, you're taking two elements from G, is equal to phi of A circle phi of B, right? Now observe, A and B are elements in G, so the product AB refers to an element in G that you get once you apply the binary operation for A and B. On this side, you have these two elements that are actually in H. Once you apply the function phi to A, phi of A is an element in H. Phi of B is also an element in H. So you have the product of two elements that are in H. So the product over here is gotten by applying the binary operation defined over H to these two elements, right? So explicitly you can denote it by uh, showing these binary operations, the homomorphism between the two groups G and H, right? So this is what it means. So what do we have here? This actually gives you a relation between the binary operations. You have two elements that are taken from G, apply this binary operation, you get, if it holds, if this equation is satisfied, you get two elements in H with respect to A and B, and the product is what you get when you apply the binary operation over H, right? So if I put it this way, we can write this actually gives a relation between the binary operations and hence between the two group structures. Right? Okay, now let's take a look at some examples. Let's start off with the trivial homomorphism, right? Let's take G, H to be groups. Then we can always find at least one homomorphism, which we call the trivial homomorphism. How do we get this homomorphism? By taking all elements in G and mapping it to the identity in H, right? So it's right, there will be at least one homomorphism the trivial homomorphism defined from G to H by sending every element in G to the identity in H, right? The G in G. Every element in G will be sent to the identity in H. Right, now to see that this is indeed a homomorphism, we have to check whether this condition is satisfied. For any two elements that you take from G, if you take A and B from G, we should be able to show that phi of AB is equal to phi of A times phi of B. Right. So let me write to see that this is a homomorphism. Let's take A and B from G. Then we have now A and B are taken from G. So AB, because G is a group closed under its binary operation, we have AB to be an element in G. And so by definition of this phi that we have defined over here, we have phi of AB to equal the identity of H. We want to show that phi of AB is equal to phi of A, phi of B, right? Now, the identity I can write as the identity EH times EH. This EH I will replace by phi of A, right? And this I will replace by phi of B. So the condition holds for any AB that you take from G. Therefore, by definition, this is a homomorphism. But this is not a very interesting homomorphism. Why? We can't, all the elements in G will be mapped to this one element in H, right? So there's nothing really special that you can retrieve, or you can't really retrieve any information about the group structure, right? So it's not very interesting. Let's look at some other examples. Let's take phi to be from R to R star, right? Defined by phi of x equals the exponential function. Here R is the additive group of real numbers. Here we have the positive reals under multiplication. So what I'm going to do is I will denote it by, I will write it, R we will write. Reals. I have taken R star. We usually take R with the multiplication sign. This is the multiplicative group of positive real numbers. So we don't have any negatives or zero, simply positive real numbers. Okay. Now, to see that this is a homomorphism, what are we going to do? We will take any two elements x and y from R. Any two real numbers, any two numbers that you have taken from this group, right? So we want to find phi of x times y. Now this is the group under the binary operation addition. So x times y would simply refer to x plus y, right? So we find phi of x plus y, right? This is equal to, by definition of phi, the exponential function of x plus y. You can write this as the exponential function of x and then y. By definition, this would simply be phi of x times phi of y. Now here you can say phi of x times phi of y. Why? The binary operation over this set is simply multiplication. So we see multiplication over here. Over here we denote the binary operation. It's addition. Therefore, we simply use addition instead of writing x times y. Okay. And this is true for all xy in R. Therefore, Phi is a homomorphism. Phi is a homomorphism. Right. Now let's take a look at the example. Let's take a group. The multiplicative group of all invertible matrices of order n, right? So this group contains all invertible matrices of order n. Binary operation is multiplication. Okay. Then we'll take the same group that we had in the previous example, multiplicative group of okay, so this is the multiplicative group of positive reals, right? Usually we denote it by, I will correct it here itself, or with this multiplicative sign, multiplication sign, sorry. Right? Over here, R star would simply denote the multiplicative group of all non-zero real numbers. Right? Of all non-zero real numbers. Right. Then we define, this is something that you actually already know, a function phi from this group to R star by taking any matrix over here and mapping it to its determinant of A, or in some other cases we denote it by this. This is also a group homomorphism, right? You take any matrix from here, you can find the determinant because you have all square matrices in this group, right? And it is mapped, and you have all matrices to be invertible. So none of them will have the determinant to be zero. So it's a well-defined function. There is no zero in this set, right? None of the matrices in this group will have zero determinant, right? It will either be a positive real number or a negative real number. We take the matrix and map it to its corresponding determinant over here, right? And to see that this is in fact a homomorphism, let's take two matrices A, B from this set and find phi of A, B. Now this is a group under multiplication. This is also a group under multiplication. So we take phi of A times B. This is equal to the determinant of A times B. We know by properties of the determinant, you can write the determinant of the product as products of the two determinants. So you can write it as this. And the determinant of A is simply phi of A times phi of B. Therefore, by definition, this is a homomorphism, right? So in other words, the determinant is actually a homomorphism from the group of non-invertible matrices of order n, sorry, invertible matrices of order n to the set of non-zero reals. Right. By definition. Right. So let's go over another example, the evaluation homomorphism. Right. Let's take f to be the additive group of all functions f from the set of real numbers to the set of real numbers. We take R in the usual notation to be the additive group of real numbers. So, right, additive. Additive group of real numbers. Now, let's fix some value C in R. Let C be an element in R. And corresponding to this C, we will define a map, define a function phi sub C from the group of real valued functions, the additive group of all these real valued functions, to R by Pc of f, a function that we take from here, to equal f of c, right? So we are evaluating this function at the point c. This is why we call this evaluation homomorphism, right? For f in f, right? Now, as a small reminder, let me write the sum of two functions. How do we evaluate some value of the sum of two functions? Sum of two functions is f plus g, and we evaluate this sum at a point x by taking f of x plus g of x. Right. Now, to see that this is indeed a homomorphism, right? Let's take two functions from f. So let's take f and g from f. Then we have phi of c, f plus g. Why do we have f plus g? Because addition is the binary operation over f now. It's the additive group of all functions. This is equal to f plus g of c. And we know how to evaluate the value or evaluate this sum at a certain value x. This is f of c plus g of c. By definition, now, by definition, f of c is given by what? Phi c of f plus g, phi sub c of g. This is by definition of this function, phi sub c. Right. And R is once again the additive group of real numbers. So that's why we have addition over here. By definition, this is a group homomorphism. It's a group of integers. Right. Now, let's take this example, this other example. Let's consider Z the additive group of integers. Right? And let's fix some value n in Z. So we are fixing a value n in Z. Then we will define a function which I will call phi subscript n. So I will call it phi sub n from Z to itself by P sub n of x equals n times x. N times x. Right? This is also a homomorphism. Right? To see that this is indeed a homomorphism, we take any two integers x and y. So let xy be two integers in Z. Then we see that phi n of x plus y. Right? Why do we have x plus y? Because these two elements are taken from Z where the binary operation is addition. Right? This is equal to, by definition of this function, n times x plus y. This we expand nx plus ny. Nx is simply phi n of x. This is phi n y. Once again, these two elements are elements in Z. This is the group under addition. This is why we have addition over here. So by definition, this is a homomorphism. It's a homomorphism, right? And it's a homomorphism for every n. This n is fixed. It's chosen arbitrarily. It's a homomorphism for any n that you take from Z. I'll put it this way over here. Now see what happens when you take n equals 0, then we have phi of 0 from Z to Z, defined by 0 times x, which is simply 0. Now this we have seen early on when we were doing examples of homomorphisms. This is the trivial homomorphism from Z to itself. Why is this a trivial homomorphism? We are taking every element from Z and mapping it to 0, which is the identity in Z, right? So I can write, since 0 is the identity, we see that is the trivial homomorphism. It's the trivial homomorphism. Now, if we take n equals 1, then we have phi 1 to be from Z to Z, defined by 1 times x, which is equal to x. You have the identity. You have the identity map. You are taking every element from any element x from Z, mapping it to itself. So when n is equal to 1, you get the identity, right? Okay. Right. Let's take a look at another example. Reduction modulo n, right? Okay, now we are going to define a map from the additive group of integers to Zn. Zn containing integers from 0 to n minus 1 under the binary operation addition modulo n, right? So let's define phi from Z to Zn by phi of m equals R. What do we mean by R? R will be the remainder given by division algorithm when we divide m by this n, right? Where R is the remainder given by the division algorithm when m is divided by n. So for example, if you look at a few examples, phi of, we had to consider a specific n here. Let's say we are defining phi from z to z6, perhaps, right? Then phi of, let's say 4 will be the remainder that you get when you divide 4 by 6, right? When you divide 4 by 6, apply the division algorithm, the remainder will simply be 4. So this will be 4. Phi of negative 4, this you can, no, let's say do phi of 24. This is equal to, because it's divisible by 6, there is no remainder. Remainder is 0, so this will be mapped to 0. If you take phi of 8, you simply have to apply the division algorithm. Divide 8 by 6, you take the remainder, you get 2. This is because you can write 8 as 1 times 6 plus 2. This is our R, the remainder. This is where we apply the division algorithm, right? Now, for the general case, to see that this is indeed a homomorphism, we have to show that the homomorphism condition is satisfied, right? Okay, so we write to show that phi of x, now this is the additive group, so let's write x plus y for any xy that you take from z equals phi of x, and the binary operation over here is addition modulo n, which will be denoted by this. Phi of y for xy in z, right? Using division algorithm, we let, using division algorithm, we let for x. Now what we are going to do is, we will apply the division algorithm to x and y to find their remainders. Those will pop up over here. So the addition of those two remainders must be the remainder that you get when you divide x plus, sorry, when you divide x plus y by n. Sorry, right? Okay. So we are going to apply the division algorithm to x. Divide x by n. So you have the quotient, let's say q1 times n. Take r1 to be the remainder. So By the division algorithm, we know R1 lies between, it could equal 0, definitely less than n, right? Y also, we have the quotient Q2, n, and the remainder R2. Once again, R2 could be 0, definitely less than n. When it's a positive number between 0 and n, excluding n. Right? Now, sorry. What I'm going to do is, using those two values that we have gotten for x and y, we take x plus y. This is equal to what? Q1 n plus R1 plus Q2 n plus R2. So we've got Q1 plus Q2 R1 plus R2. Now what I'm going to do is, I will apply the division algorithm to R1 plus R2 when it is divided by n. This is because R1, R2 are two integers. So this addition is also an integer, right? So let me write now, R1 plus R2 is an integer, right? So using the division algorithm, we see that R1, R2, when you divide it by n, you get a quotient of Q3, let's put, and a remainder R3, where R3 actually lies between 0 and n, right? Between 0 and n. Now going back over here, we have x plus y equals x plus y equals, we have q1 plus q2 times r1 plus r2 we can replace by this one. So we've got q1 plus q2 plus q3, considering this value n plus r3, adding, replacing r1 plus r2 by this over here, right? Now observe, uh, this equation tells you R3 is now here. R3 lies actually between 0 and n, right? So this equation tells you when you divide x plus y by n, the remainder must be R3. Remainder must be R3 because it's a value that lies between 0 and n, right? Therefore, from here we see that phi of x plus y must equal R3, right? And we know that phi of x is equal to R1, phi of y is equal to R2. Now we want to show that, R1, now these two, observe, are elements in Zn. These two are definitely elements in Zn. Why? Phi of x is equal to R1. Phi of x is an element in Zn. Phi of y is an element in Zn. Now observe R1, R2, those are positive integers between 0 and n, never equal to n. So we can easily see that these two elements are in Zn. We want to show, in order to prove that, sorry, phi of x plus y is equal to phi of x, take addition modulo n phi of y, we want to show that R1 addition modulo n R2 is actually equal to R3. And that can be easily seen from this equation. how do we find let me put it as 1, right? By 1. We see that R1 addition modulo n R2 is in fact R3, because how do we calculate this addition? You add these two numbers R1, R2, divide by n, take the remainder, that is addition modulo n. Exactly what's seen over here, R1, R2. When you divide by n, you get a quotient Q3, and this is the remainder, which is also another number between 0 and n, right? Therefore, we have phi of x plus y to equal R3, and this is equal to phi of x, addition modulo n, phi of y. Right. Therefore, phi, by definition, is a homomorphism. Yeah. Okay. Okay, now let's come back to D3 and S3, right? Let me write it on the side. First, we are going to define a homomorphism between D3 and S3. Right. Now, recall that any element in D3, any element in D3 can be written in the form mu1k rho 1I for k equals 0 or 1 and I between 0 and 2. Similarly, we actually saw this early on. Similarly, any element in S3 can be written in the form 2, 3, which corresponds to mu1, k, 1, 2, 3, which corresponds to I, for k equals 0 or 1, and once again, I between 0 and 2, right? Now let's define, once again, let me remind you the relations. No, let's go back to our note and we'll see that. Okay, now these are the two relations for rho 1, mu 1 in D3, right? We have a very similar relation for, we simply have to replace mu1 by the corresponding element in S3, rho 1 by the corresponding element in S3. So you can write, over here you have the relation similarly, we have here 1, 2, 3. This cycle raised to the power of 5, 2, 3 is the same as 2, 3, 1, 2, 3, raised to the power of -1. Right, so we will be using this relation as well. Okay. Right. Now let's define um, P from D3 to S3 by um, two, 3i. Right? What exactly is happening over here? We are essentially mapping the corresponding generator. Mu1 will be mapped to 2, 3. Rho 1 will be mapped to the cycle 1, 2, 3. Right? So let me write it. We are essentially mapping mu1 to 2, 3 and rho 1 to 1, 2, 3. Now, to show that this is indeed a homomorphism, we have to take any two elements from D3, right? So let's take AB elements from D3, right? Then we have any element in D3 is written in this form, right? Is written in this form. So for some K1 and for some I1, we can write A as mu1, let's go with K1, rho 1, I1. And B can be written as mu1, K2, rho 1, I2, right? Where K1, K2, either 0 or 1, and I1, I2 will simply be between 0 and 2. Right. Now, let's calculate AB. AB is given by mu1, K1, rho 1, I1, and then we have mu1, K2, rho 1, I2. Okay, right. Now, what I'm going to do is I will consider two cases for K2. When K2 is equal to 0, because K2 can only be either 1 or 0. When it's equal to 0, right? Let me write over here, K2 is either 0 or 1. So when K2 is equal to 0, we have AB to be, now this K2 will be 0, mu1 raised to the power of 0 is simply the identity function, identity permutation. We have mu1 K1, rho 1 I1 times rho 1 I2. This is simply what? Mu1 K1, rho 1 I1 plus I2, right? Rho 1 I1 plus I2. So in this case, for this particular case, when you calculate phi of AB, we have phi of mu1 K1 times rho 1 I1 plus I2, right? This is actually easy to understand that this all works out because you see these generators are mapped to each other corresponding, right? Now let me show you the proof anyway. This is equal to, by definition of phi, 2, 3 to K1 and 1, 2, 3 to I1 plus I2. This you can write as 1, 2, 3, I1 times this cycle raised to the power of I2. Right? Before I write that, I will write 2, 3 raised to the power of 0, which gives you the identity. So you can write it. Right? And this is equal to what? K2, because in this instance, K2 is equal to 0. Now we have from this composition, we get phi of this is K1, sorry. Phi of A times, from here you get P of B. Now the other instance when we have K2 equal 1, right? Sorry, K2 to equal 1. When K2 equals 1, we have K2 equals 1, we have AB to be mu1 K1 rho 1 I1. Then we have mu1. K2 is 1 now. So this power, we have the power of 1, which is simply mu1 rho 1 I2. Now what are we going to do? We will apply that relation to these two elements and write mu1 K1 is simply what? Mu1 rho 1 negative Y1 rho 1 I2. This is equal to mu1 K1 plus 1 times rho 1 negative I1 plus I2. Now we apply the function phi. Now we have phi of AB to equal phi of mu1 I1 plus 1 rho 1 negative I1 plus I2. By definition, this would be 2, 3, I1, sorry, K1, K1. This is K1, sorry about it, K1. K1 plus 1. This is 1, 2, 3, negative I1 plus I2. So we write it 2, 3, K1, 2, 3, and then we have 1, 2, 3, negative I1 times 1, 2, 3 raised to the power of I2. Now once again we apply the relation to these two, right? We get 2, 3, K1, permuting these, and we send this power to its negative counterpart. So negative gives you a positive. We have 1, 2, 3, I1 times we've got 2, 3 times 1, 2, 3, I2. This power 1 over here is actually what? Equal to K2, because in this instance, this is equal to K2. This over here is simply phi of A times phi of B. So in any case, we have phi of AB to equal phi of A, phi of B. Therefore, this is a homomorphism. This is a homomorphism. Right. Now let's take a look at some properties of homomorphisms. Okay, let's take G and H to be groups. And let's take phi to be a homomorphism, a group homomorphism from G to H. Right? Then if we have G to be abelian, H must also be abelian. That is one property, right? If G is abelian, then H must also be abelian. How do we prove it? Let's take any two elements, A and B from H. Let A, B be in H. We just have to show that in order to show that G is abelian. Now these are chosen arbitrarily, right? If we show that these two commute, AB is equal to BA, then we are done. That proves that H is abelian. We need to show that AB is equal to BA. So let's start now. A, B are in H. Right now, we have to have one condition over here, condition imposed over phi. This has to be an onto function. For each element in H, there must be a preimage in G, right? So let me put it over here. Be a homomorphism. Mm, which is onto, let's say, right? Which is onto, right? Now let me write, since phi is onto, for any element A in H, any element AB in H, we must have some element in G which maps to those elements through the map phi, right? There exists xy in G such that phi of x is equal to A and phi of y is equal to B, right? Now, let's calculate AB. AB is equal to phi of x times phi of y. This is equal to phi of xy. Why is that? Phi is a homomorphism, right? Because this is a homomorphism. It's a homomorphism. Now, this is equal to phi of yx, y times x. And why is that? This is because G is an abelian group. So any two elements you can commute. This is because G is abelian. Right? And once again, phi is a homomorphism. So we have phi of y times phi of x. Phi of y is simply B. A. Exactly what we wanted to show. Okay. Let's go over this theorem now. G to H. Be a homomorphism right? Then we have the identity in G will be mapped to the identity in H. Phi of the identity in G is equal to the identity in H. And then we have phi of G inverse for any element G in G must be phi G of inverse. And then we have the order of this element is equal, this divides the order of G. For all G in G, this is if the order of the element is finite. Order of this element is finite. Okay. Let's prove the first one. Okay, let me write since this function is a homomorphism, we have for all xy in G, x times y to equal y, right? I'll take this to be 1. In order to show that the identity is mapped to the identity in H, what we are going to do is, in 1, we will take x and y both to be the identity in G, right? So what happens in that case? We have x to be the identity, y to be the identity. Identity times the identity gives you the identity. And then over here, so for 1, let me show you by letting x equals y equals the identity on G, we get times the identity equals and this is simply the identity. So this has given you right. Now what do? We take the inverse of now. This is an element. This is an element in H, right? This is an element in H. So what do? We take the inverse of this element on both sides, on the right or the left, it doesn't really matter. To see that, let's take the inverse of this element on the right. This will give you, because these two are elements in H and one is the inverse of the other, we have this to be the identity of H, right? This also the identity in H, and this gives you identity in H equaling any element times the identity will give you the element. So it gives you by this function, EG is mapped to EH, the identity in H. Exactly what we want to prove. Right now, to show that the second one holds, what we do is we will take in 1, we will take x to be G and y to be G inverse. When you do that, what happens over here? We have in this product G times G inverse, which gives you the identity. And we know the identity through this homomorphism will be mapped to the identity in, oh, this has to be, sorry, I have made a mistake over here. This has to be the identity in H. Okay. And then over here we have, right, let us write, let's take in 1, letting x equals G, and for some element G in G, this is, okay, and y equals G inverse. In 1, we get G inverse equals phi of G of G inverse. This is simply the identity of G, right? All these two elements are taken from G. So we've got the identity on this side. Now this by part 1 over here will be mapped to the identity in H. Now what do? We will take the inverse of this element on both sides to see that. And on the left, we see that your left will reduce to the inverse of this element. Over here, it will simply be, oh, where is it? Okay. Psi of G inverse, right? So this will simply be, and this giving you the identity over H, identity times the element, you get the element itself. Exactly what we want, exactly what we wanted to show. Okay.